Hi, we start the fourth module in this lecture. In the fourth module, we discuss the passband transmission. The digital modulation systems may be broadly classified as two: coherent and non-coherent systems. The coherent system requires phase information for the detection of the transmitted signal. That is, I transmit my message, and in the receiver I need to know the exact phase of the transmitted signal to do the detection. Hence it needs a complex circuitry for phase tracking, because transmitter and receiver should be in a phase locked loop. So it's an expensive kind of detection process, but it's a better detection. In non-coherent, we do not require the phase information, so it's a simple detection process. Now the transmission model, we have two types of transmission models, that is baseband transmission and passband transmission. In baseband transmission, we transmit the data directly to the channel. We do not have any carrier here. We do not modulate the data to the carrier. For example, we have pulse amplitude modulation, pulse chord modulation, studied in the first module. In pulse amplitude modulation, we sample the data, sample the analog signal using a series of pulses. Okay, and that pulse train is then transmitted. In pulse chord modulation, what we do, we sample the data, quantize, and then convert that to a series of beats and then transmit. In both these transmission models, we do not have a carrier. Now comes a passband transmission. Here the data is modulated to a carrier, generally a sinusoidal carrier, and then transmitted. That is, this is my baseband signal. Okay, now I modulate my baseband signal to a carrier. So this is my carrier. Okay, I modulate my message to the carrier. Okay, so this is the passband signal. Okay, this is passband signal. Passband transmission model. Here I have a message source which has m message symbols to transmit, namely M1, M2, etc. up to mm. Now this message source emits one of this m message symbols in every t seconds with equal probability. Okay, so each symbol has a probability of getting transmitted equal to 1 by m, because we have m symbols to transmit. Assume that it's a binary source, for example, then I have only here m, capital M is equal to 2. That is, I have only two symbols to transmit, either 0 or 1. Okay. Next is a signal transmission encoder. The signal transmission encoder converts or encodes my message symbols corresponding to the encoding scheme that I have used. For example, if I am using polar non-return to 0 encoding, then the message symbol 1 will be converted to a pulse of amplitude A, and 0 will be converted to a pulse of amplitude minus A. Okay, or we can say it generate a signal vector Si corresponding to the message symbol Mi. Here my signal vector is one dimensional. Okay, now I have a modulator. Here this signal vector is converted to a modulated energy signal Si of t, and then this Si of t is transmitted to the channel, where in the channel a noise is getting added, and we have modeled the channel as additive Gaussian noise, white Gaussian noise channel. And in the receiver we have a detector, because we have a modulated here. Detector is a demodulation operator. So I have a modulator here, then I have a detector here, which reverses the operations performed by modulator. Now before the modulator I have an encoder, then I'll have a decoder here, and at the output of this I'll get an estimate of the message symbol that I have transmitted. This is in general a passband transmission model.